Are we live? Are we live? Are we live? Yes, we actually have very good audio. Very good audio. Best audio. Oh, we're up to 176 subscribers. We need to celebrate. I think we should celebrate. At this point, we should celebrate each subscriber. Let's celebrate with a song. La 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 la. La 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 la. La 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 la. Can you guess the song that I'm singing? Ali la la. Okay, so today I want to do something. So the title of today's show. Well, let me take the link. The link. Come on, come on. The link to today's show and put it in the side chat. So if anybody joins, they see the link. And let me take the link to our great Discord and place it. Oh, we already have someone with us. Hello, Mr. Slave. Hope you're doing well from Slanash's disciple. La la la. Hello, sir. Here's the link. Anyone can join us on the Discord. We would gladly entertain you on our great Discord. All right. So today, the title is Let's Prove Relativity's Postulate. Constant speed of waves in a medium in a bathtub. So this is I went last night. I went to a very nice place, nice party, and I took some time and I sat with a paper and pen and I started thinking and drawing how are we going to prove a postulate. So that's a contradiction. You don't prove postulates. A postulate is an assumption. So, but we want to prove a postulate, so we will remove it from the list of postulates and make it a proof, make it a theorem. So, but as I was trying to accomplish that, I realized that I really need to understand the geometric cause for length contraction. So time dilation is very straightforward. But length contraction, not so much. So I want to see how people prove length contraction. But length contraction, so of course we're doing this in a bathtub, so we need a geometric length contraction. Why is there a length contraction according to relativity? But I don't care for a I don't care for a physical length contraction, only for the optical effect. It's not an optical illusion because it actually has effects. Because if something appears to me to be contracted lengthwise, that means it has a greater effect on me. So imagine a very, very long string that is, it doesn't weigh much, a hair, a very, very, very long strand of hair, right? It's almost weightless. It's very long, miles and miles and miles long. So altogether, it's very heavy. Altogether, it weighs, let's say, trillions and trillions of tons, right? It's floating in outer space. It's a strand, it's a very long, either strand of hair or even a spider, not web, but just a single strand of a spider silk strand. But it's very, very, very long, like trillions and trillions and trillions of miles. So it weighs trillions of tons. But when it passes by me, there's very little of it. But let's say now it's traveling faster and faster and faster relative to me. So it's actually going through length contraction relative to me. I am experiencing it. I am experiencing an optical effect that is being contracted lengthwise. Okay, so it's not an optical illusion. It's an optical effect. So what's the difference? The difference is that this is measurable. It's actually, as far as I can measure, it is compressed, and it's heavier and heavier as it's moving faster and faster. It appears to be more and more and more massive because more and more of its length is being length contracted, so that it appears to be more and more and more massive. This could reach even the mass of a black hole. This could become, in my frame of reference, this could be a black hole. This is fascinating. So a black hole is just a point of view. You didn't see that coming. Even in a bathtub, right? The last thing you expected is to experience a black hole in a bathtub. So how would that happen? Well, if it's traveling very close to the speed of the medium, then it appears to be completely contracted. So let's say it's a very 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 long bathtub. It's trillions and trillions and trillions of miles of a bathtub. Okay, and there's a spider strand passing by me faster and faster and faster and faster. But now wait 1 second. That's impossible because that's a particle, and we're not looking at a particle, so we don't know what a mass is. So I don't know how to do this. So I don't know how to do the mass calculation or the whatever. So we'll come back to looking at mass. Let's ignore mass for now. I didn't get there yet. Right now we want to look at length contraction. Anyway, the length would appear to have been contracted, and whatever is implied by that. And for now, it's just a length. So let's go watch some videos of people who have discussed length contraction. Length, let me see the number of subscribers. It's very nice. I don't care about this guy. Lorentz, rocket and string paradox. I don't care so much for a paradox. This is today's video. Okay, let me open. Here is a tab. Let's watch this. Let's see, we have a message here or a notification. What does it take? Okay, whatever. Okay. So the next thing I want to watch is length contraction. So let's talk about length contraction. We want to see the proof. I want to see the proof of length contraction. Professor Dave explains. I don't like the way he explains. He explains things like they're obvious, but he explains really, really advanced stuff in an obvious manner. I don't know if I like it so much. Now, time dilation was pretty weird, huh? Well, we aren't done yet. Time is relative, and so is space. Different observers. Okay, let's give him a chance.
Is time moving at the familiar rate and can measure some distance for the journey, which we length contraction.
He knows a lot about the science stuff.
Einstein's special relativity was a huge step in physics. And even though time dilation seems like the weirdest thing you've ever heard, there's plenty more to get through with this theory. As it happens, it's not just time that's relative, it's length as well. And as we will find out, the math tells us that when you approach the speed of light,
I don't like it when people say the math tells us. Math is a language. A language doesn't tell you. A language is just one way to share ideas. That's all it is.
measurement of space changes.
You could say it's a way of remembering things, right? You can use language for many things, but I wouldn't say, like, you can write an essay. Math is just a shorthand.
Just like time. This is because if an observer on Earth and an observer
And he's showing again the engines running. You, in special relativity, you should not show engines running. It's a violation of special relativity. Special relativity and length contraction is a discussion in inertial frames of reference. So inertial means inertia, meaning no acceleration, meaning no engines should be running, and neither should there be a planet with a gravitational field. So that's not a good idea. You should avoid these images. So I don't know. It's already like a bad start. So let's see what he says here. How much time passes less? What do you mean less? What do you mean less? More. What do you mean more? Oh, he's stationary relative to this guy. This guy is moving. Yeah, but it's a symmetric discussion, right? So because the engines are not running, so the guy in the ship looks at the guy on that is stationary, quote unquote, but it's a symmetric view. You can split it down the middle, and each one is looking at the mirror. So this guy sees this guy moving by, and this guy sees this guy moving by. Now they should each be seeing each other's clock ticking slower, which sounds like a paradox, and we need to resolve it. But that is if you put these two people in the bathtub, the two clocks moving past each other, they will see each other. Each clock will see the other one. Well, they should see each other ticking slower. We still need to prove that. We we haven't discussed two observers moving past each other. A little bit. I didn't do the math. I didn't do any derivation. I don't think. But if since in a bathtub we have a a motionless point of view, in the bathtub we have an absolutely stationary observer. But the way you're supposed to conduct the experiment with the bathtub is with an infinite bathtub and in the dark. So you should not know that you're stationary. You, as the observer, is stationary in reference. Now you could run an interferometer and discover your motion relative to the medium. With an interferometer, you can discover. This is a violation of Einstein's happiest thought, by the way, and also I think Einstein's or even Galilean relativity that say that you cannot know who's moving. There is no absolute frame of reference. Well, there is. I don't know what absolute means, but there is a frame of reference, a preferred frame of reference that is the ether or the water in the bathtub. That you can discover using an interferometer. You can discover if you're stationary or moving in whichever direction. It's discoverable. Yeah. Yeah. Oh, 1 second. I need to turn on my phone because I'm expecting a delivery. Okay. It's being prepared? It said, oh, one. Okay. So, like in 10 minutes, it should be here. Okay. Anyway, so there's so much stuff confusing here. Okay, let's continue. Let's hear what he says. Okay, the observers measure different spans of time. Okay. Okay.
Observer in a fast spaceship register different spans of time for an event, they must also be recording different distances.
So he's saying pretty long. I don't know what he means. I don't know what he means. Like, who says what about whom? The observers must register different lengths. Why? He didn't. Okay, this is useless. Like he's. I don't. I cannot understand his graphic. So forget it. Okay, length contraction and time dilation, special relativity. So I was thinking this contraption might actually be useful for us. This might simplify everything. But this is chapter 5. I don't know if we're going to be able to understand it.
Transformation, which is a kind of squeeze stretch rotation of spacetime that I've mechanically implemented with this spacetime globe. Two of the most famous implications of Lorentz transformations are phenomena called length contraction and time dilation. And while their names make them sound like they're two sides of the
They never explain who Lorentz was. Why did he? I mean, what? How is he related? They never discuss Lorentz. They discuss Lorentz time dilation, Lorentz length contraction, but they never tell us who Lorentz was, why he said what he said. It's really weird.
one or in our universe, when you change from a non-moving perspective to a moving one, or vice versa, that change of perspective is represented by what's called a Lorentz transformation, which is a kind of squeeze-stretch rotation of spacetime that I've mechanically implemented.
So I think this contraption was created by Minkowski, who was Einstein's teacher or something.
With this spacetime globe. Two of the most famous implications of Lorentz transformations are phenomena called length contraction and time dilation. And while their names make them sound like they're two sides of the same coin, they're definitely not. We'll start with time dilation, which is easier to see. Suppose I have a clock with me that ticks every 2 seconds, but if you're moving...
Forget it. Forget it. I mean, he's using the contraption right away. No, I'm not interested.
Like they're two...
Let's consider another one of Einstein's thought experiments to uncover a new concept.
Okay, let's see this guy. In general, I would say he's maybe the best. Years ago.
I've spoken about special relativity for quite a few videos, and I'm going to stick with that subject matter here too. The last handful have focused on relativity basics and how clocks tick differently for different observers. But there's another counterintuitive consequence of relativity that confuses the heck out of people. This is the idea that different people see lengths differently. I mean, how can that possibly be? I bet you know that I'm going to tell you because, well, you guys are smart that way. Before I start, I should tell you that this video has an actual derivation. Sorry about that. But it has something even more important. It first uses relativity wrong, but in a way that seems right. Then I identify the mistake and redo things properly. This is a super important thing to see because it's so easy to make mistakes in relativity.
Fascinating. So you see, already he's off to a good start that he says everyone gets confused, everyone gets it wrong, you have to be extra careful. That's the way you should teach. I think you should always say, well, this is really tricky, it's really hard. If you get this, it's going to be very impressive. And most teachers and parents do the reverse. They say, oh, it's so simple. By saying something is simple, you're scaring the student. You're scaring me. Like if I don't get it, then I'm a dummy dum dum. And that puts pressure on the student. So you think you're causing the student to relax by telling them, "Oh, it's so easy," and then they end up not understanding, and then they feel dumb and they lose motivation. Now, this guy works at Fermilab, so he's an actual researcher. He actually runs experiments. He's an experimentalist. So already I have much more respect for him than for theoreticians. Like, as far as I know, he actually measures things, which theoreticians usually don't. Theoreticians usually never see the things they talk about. Okay, let me see the update. It's being delivered in 6 minutes. That's good. That is good. Let's continue. Ba-ba-ba-ba-bam. Lorentz transformation. So I think x2 is the length. The length is contracted, and the time, I don't get it. This is also contract because this is isn't this is always less than one. This is the square root. It's not one over the square. This is the square root. Lorentz transform. Some people call it transformation. Some people call it transform. So I don't know what this is. I don't know what that is. I don't know. I don't know what this is.
The good thing is that the math is pretty easy. We just start out with the standard Lorentz transform equations. As a reminder,
We start from Lorentz transform.
those are the equations that you see here. If you've not seen them before, I talked about them in my video on what relativity is all about. Take a look at that video if you like, or you can just trust me and we can press on.
No, we need to see the derivation. I don't understand what Lorentz transforms are. Where's the link? Lorentz. Why does light slow down in water? So how do we get to that video? How do we do that? He didn't give us a link.
Make mistakes in
Oh, maybe that's a link.
The good
No,
thing
it's
is
not a
that the
link.
math is pretty easy.
Not a link.
We just start out with
So maybe somebody gives us a link here. I finally blah 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 blah. Come on, someone must link it, and it should get so many likes. But apparently, no one links it. No one asks for it. Oh my god! Let me go through. Let's load more comments and then look for the word link. Okay, Control F, link. No, no link. So no one ever asked for a link. So you want to tell me everyone who commented already saw the other video? How did you find it? Nothing. Okay, I don't believe it. I don't think anyone understands this. Let me see. One of the most gifted. I finally understood. I love this guy. I've been trying. I like how. Way cool. I misunderstood. This channel. I understand, Mr. Lincoln. Answer. This happens when a man. Physics is. I bet. I like. I thank you. Yeah, I don't believe anyone understands anything. That's nonsense. Okay, let's find this video. So we want Fermilab Lorentz transform. Okay. Oops. Fermilab, I would say channel. Can we look? Can we do a search in Fermilab channel? Is there a search? Yeah, here's a search maybe. Lorentz. Relativity key concept Lorentz gamma. Okay, so this would be good because then maybe length contraction comes next. Okay, let's go here. La 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 la. All right, let's go.
He starts the stopwatch and shines the flashlight across the car into the mirror, which then reflects.
Starting over.
I've done a couple of videos about relativity, and I'll do some more. I guess you could say that I'm on a relativity kick. In one of my videos, I showed that relativistic mass wasn't real. It's just a pedagogical device that has some value in terms of building intuition, but ultimately is more trouble than it's worth.
Let me just make sure that our audio is good. Let me make sure that we can hear Dr. Don. Yeah, it's good. Audio is good.
In the comments of that video, people asked about the physical meaning of the gamma term in the momentum equation. By the way, another term for gamma is the Lorentz
1 second. Being delivered in 6 minutes. Okay.
factor.
Oh, this is the Lorentz factor. So we've seen. What is their name? What is their name? Their name dialect. So we saw dialect developing gamma from the sound clock. They actually also developed length contraction without discussing it. You know what? Let's go look for that video at the end without explaining. They they're called dialect sound clock. La 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 clock around the world. How other language. This one. This one.
This means there's no way to tell if our clock is ticking in accordance with true universal time, or if it is ticking at a dilated rate. Meaning it is not time itself which is relative, merely our knowledge of it.
Yeah, it's not even our knowledge. There is no time. There's just ticking. And our brain is the ticking. Oh, hold on. Somebody's at my door. That's earlier than I expected. Give me a minute. I'll be right back. Uh, Can you hear me? Can you hear me? 1, 2, 3. 1, 2, 3. Can you hear me? 1, 2, 3. 1, 1, 1. Yes. The microphone is malfunctioning. Okay, but I ordered a new microphone. I have at this point about 10 microphones. They're all worse than each other, paradoxically. Okay, let's check that the audio is still functional. Is the audio functional? 1 second, let me check. Let me check. Yeah, audio seems to be okay. No messages. We're good with messages. Everything is good. Good. Okay. Everything is fine. Let's go. 3, 2, 1. Oh, Joe's incarnate. How are you? How are you, Joe's? You want to join us? You have the link. If you want, you may. Okay, let us continue.
Now, this precipitates an epistemological conundrum of sorts, because any uncertainty in time based measurements will propagate as uncertainty in other types of measurement.
So, time, length, and velocity. Yeah, good. That's what I was thinking. How do you know the velocity?
For instance, given a known distance,
Okay. All right. Given a known distance, right? So I am the observer. So I can measure my distance. So I know I can measure, like, let's say this is the bathtub or sound wave. So as the observer, you have to assume that you don't have eyes. You close your eyes. You can't see anything. So all you have is the waves. So all you can sense is the waves. So okay, but you can measure your own length. And it says here 1 c second. This is, how's this length? I don't know what they mean. And clock start stop.
we'll find that any judgment of velocity will be subject to the uncertainty of our time judgment, since moving observers would unknowingly judge their velocities to be greater.
Okay, this is really confusing. So moving observers will judge velocities to be greater. Why? How can I judge my velocity? How can I measure, right? Everyone thinks they're stationary. Why would I? So he claims that let's try this again.
Given a known distance, we'll find
So given a known distance, according to whom? Who knows the distance? What do you mean known distance? Who knows the distance? Known to whom? I don't understand.
that any judgment of velocity will be subject to the uncertainty of our time judgment.
So there's two velocities here. There's two clocks. There's this length. This robot works on the sound clock. His brain is okay. Joe's has stuff to say. I'll see if I can get back to you later on my way out. Hope you like the song. No, I don't like songs. I don't like songs in general that have a message. I don't like songs with message. And this only happens at relative velocities, LE, I guess, i.e. when you are using the gamma function. Yeah, but what happens at relative velocities? And it's not true. Try it. It's in your chat. What? Try what? In my chat? Where? What? What are you talking about? Try what? What's in my chat? Discord. What's in my Discord? The song? I didn't like the song. I heard it. I didn't like it. So, what? Okay. So, John, stop, stop, stop. I can't follow this conversation. We're gonna be like it's two deaf people talking. So, just whenever you can, hop on, hop on. We can have a normal discussion. Otherwise, I'd rather kill myself. Anyway, I'm confused as to what this video is saying.
For instance, given a known distance, we'll find that any judgment of velocity will be subject to the uncertainty of our time judgment.
Okay, there's two clocks. What are these two clocks? This one measured 5 ticks, this one measured 4 ticks, but they're both stationary, so I don't get it. I honestly, I have no idea what they're trying to say.
For instance, given a known distance, we'll find that any judgment of velocity will be subject.
Why is the right clock ticking faster than the left one?
To the uncertainty of our time.
I have no idea what's going on. Now, delta x, who knows delta x? Delta t, that's fine. You can measure, each one measures the number of ticks. I don't know what they're saying.
Judgment. Since moving observers would.
Okay, so the velocity is c divided by 4 ticks. What is c? C is the distance? Why c the distance? Usually c is the speed of the waves. I have no idea what's going on.
Unknowingly judge their velocities to be.
Moving observers will judge velocities to be greater. Why? Why is that? Well, it's because their consciousness is slowing down. So when my consciousness slows down at a certain speed, I feel faster because my sense of time, my perception of time slows down as my actual speed is greater. So I would perceive even a greater speed. So as I get closer to c, to the speed as my clock, as I am the clock, as I clock am getting closer to the speed of waves, c, I feel much faster than that speed at which I am from an absolute from the medium's point of view. So with an interferometer, we can determine what is a stationary position, a stationary observer. So stationary observer can know that they're stationary when their interferometer shows no interference in 3 planes. Once we find that, right? So we run the interferometer and we see that ether is flowing through us, or medium. The medium flows through us. Don't say ether, because we haven't proved the ether yet. The ether is a theory, so it's fine. But so I can measure as an observer. I can measure with an interferometer my motion relative to the medium. Okay, then I can slow down until I become stationary. Okay, at this point I can say that my observation is unimpacted by any motion. Any motion. Okay, but as I start accelerating, let's say I change velocity, one constant velocity to another constant velocity to another constant velocity. Each time I'm going to have a constant velocity. So I can look at my interferometer and I can measure my speed relative to the medium. Okay. And then I know that my consciousness, which is based on the medium, has slowed down. And any length that I seem to be passing by, I have to assume it's actually longer. Can't be because I pass by it very quickly, but that's because my consciousness is slowing down. So in the beginning, as my speed is close to zero relative to the medium, to the speed of waves in the medium, then I'm not so impacted. I'm beginning to become impacted. My consciousness is slowing down. As I get close to the speed of the waves, my consciousness has basically stopped, almost stopped. So my consciousness has almost stopped, and I should be seeing the universe. I mean, length contraction is the first thing that comes to mind. I must be seeing the universe with the length contracted because I am moving, I feel like I'm moving so much faster than I actually am. I actually, as I get closer and closer to the speed of the waves in the medium, the infinite bathtub that is an infinite universe contracts to zero. So if it's infinite, it's not going to contract to zero, but it contracts. So a person traveling close to the speed of waves in the ether, let's assume ether, his consciousness would be almost stopped. So let's say, okay, he's traveling at the speed of the ether, which is the speed of the velocity of waves in the ether, which is about 300 million meters per second. But he's going to be aware of a much greater speed. He's going to feel like he's zooming past the entire visible universe in a blink of an eye. And such a person can traverse the visible universe in a blink of an eye. That comes out of wave mechanics. If we assume the brain works on the waves. So just from wave mechanics, it looks like length contraction comes about, but still haven't derived it. But intuitively, this is what it feels like. I don't know what this animation comes to show.
Greater. Conversely, given a known velocity, it then becomes.
What do you mean given a known velocity? According to whom? Who knows the velocity? Who knows? I don't understand who's knowing this. So x, we don't know x, but we know the velocity. This is a major problem. How can we know the velocity? I mean, all we know is what looks like the velocity. I was thinking about this last night. Let's continue.
Judgments of distance which suffer this uncertainty. Since moving observers traversing such distances would unknowingly judge them to be shorter.
That makes sense.
Which brings us round to our essential conclusion. When we derived gamma for our sound clocks, the V and C stood for velocities with respect to our medium of air.
Mm-hmm. Yeah, how do we know this? How did we know V? Who knows V? We never thought about this. We just assumed V. But how can we know V?
Air. And subsequently, all our use of these quantities represented measurements that were certain. But in Einstein's gamma, the V and C stand for velocities with respect to the observer, not the medium. So if any manner of uncertainty can be shown to have crept into these values, it will reflect across every other type of measurement the theory.
Yeah, definitely. we don't know what c is, and we don't know what v is. How can I know my velocity? How can I know the velocity of the wave if I know that my consciousness is impacted by my velocity? And how? So c I don't know, but how can I ever know v? Well, it depends on traversing x, but how do I know x? That should also be impacted. Everything should be impacted. So how can I judge anything?
Theory has to offer. Indeed, it is this clue which will point us towards unraveling the remaining mysteries of relativity. Mysteries such as length contraction or the relativity of simultaneity, placing us just steps away from being able to give physical intuition to the entirety of the theory. Meaning very soon, for the first time, we will be in possession of an interpretation that doesn't rely on mathematical abstraction. Now, a huge shout out here to our Patreon.
Anyway, that was just a little taste of what I'm talking about. That was not exactly what I was looking for. Yeah, okay, Jaws. See you later. They have their reference frames wrong, lol. I'm out, hopefully later. Bye bye. They have their reference frames wrong. I don't know. I honestly don't know. We need to continue. I need to hear more. I need to hear more because this is much more confusing. Much more confusing than you would think. Like it's not clear. Like the way I would think about it. Way I would think about it. Okay, here. Oh my god. Okay, let's create a new one. The bathtub. Bathtub. Bathtub measurement. The problem with the bathtub measurement. Let me show you. Intuitively, you would say, well, what's the issue? It's so simple. I mean, there's a bathtub, there's a rubber ducky. How difficult can it be? So it could be very difficult. Very difficult. So here is the bathtub from a top view. Okay, this is the bathtub. Now, we have to close our eyes. We can't see, right? Because we want to be able to. This has to be true in every medium, including a real one that impacts our brain, like the ether. Because the ether is flowing through our brain right now and is impacting our brain. Okay. So, okay. So we have to do this experiment with our eyes closed. So, but what are we allowed to know? What are we allowed to know? So I would say all we can sense, we could have a little buoy here that is sensitive to waves. So if there is a wave incoming, our buoy is going to go up and down. It's going to bob. Our buoy is going to start bobbing. We can connect it. We can feel it. Let's say we can feel it, and we can even display it like with a pen, so we can see it. If it suddenly goes up and down, we will see it. But that's all we can see, and that is all that our eyes can see. So we should be able to see this. Sometimes we should be able to see maybe different wavelengths, like faster waves. Maybe. I don't even know if that ever happens. Because we don't care about the Doppler effect. I don't care about Doppler. So I'm going to assume that whoever is there, let's say there is, right? I can assume that there is a boat here. This boat is causing waves both from the back and from the front as it's moving forward at velocity v. Now, I don't know, I cannot know that there is a boat there of length L with velocity v. I cannot know that because all I have is this sensor. All I have, let's say, is my eyes, and my eyes are just this sensor that bobs when light comes in. That's all it does. Light is just a wave and it's just waving, and I have no idea what's going on. Now, I don't even know if I'm stationary or I'm moving. I don't know. I don't even know if the water itself is flowing here. How can I know that? So I can know. I can build an interferometer and right, send waves this way, split the waves this way and this way, capture them on the way back, this way and this way, and then see any interference when they finally merge, see any interference here, for example. And then I would rotate it and find, I would see how many ticks and so on. So it is possible to know, an interferometer can tell you the speed of the medium. And it can tell you if the speed is zero. So we should be able to know with an interferometer, we should be able to know that we are a stationary observer. But that's not even, I don't even think that's important. It's nice, but it's not important. We can just assume that we are stationary and see what we get, because this guy should be able to assume that he is stationary and see what he gets from us. Let's say we are a stationary boat that is bobbing. Let's say we are, right, this boat is attached rigidly to the bank of the bathtub. Let's say it's finite. It's a finite bathtub, but there is a boat tethered firmly, rigidly, but it is bobbing up and down and is sending waves from its front and from its back. So this guy similarly is going to have a detector. So it's going to be a symmetric view. So whatever he sees about us, we see about him. But he sees, so we see him moving to the right, we would see him, we see him, let's say, moving to the right, therefore he sees us moving to the left. So it's a mirror image, sort of mirror. It's an opposite but equal image. So he should say whatever we say about him, he should say about us. He might, regardless of the usage of an interferometer. Interferometer is nice to have, but it shouldn't really impact our discussion. So our boat or our sensor will get his signals and will be able to surmise something about his velocity, his length, right? That's it. His velocity and his length, and therefore his time, right? He has, let's say, he has a clock that is waving up and down as he's moving through the water. And the water goes right through the clock and impacts the ticking of his clock. So we should be able to infer his time. So we should be able to infer the rate of his ticking, his velocity, and his length. We should be able to infer those, or should we? I don't know. We don't know. We need to just think about it, try it. And he should be able to do the same about us, and we should both get the same results. And how do we know who's right? It's not really important. As long as we don't get a paradox. Okay, now we also could run the interferometer, and he could too, and then he'll see that, everything's fine, but regardless, there should be no paradoxes, of course, because it's just a bathtub. How can you have a paradox? A bathtub paradox would definitely make no sense if you get the right answer, right? So let's say that somebody actually is watching. So we are in the dark. So we, in this experiment, would be in the dark. But let's say there is somebody actually watching this experiment, and he knows that we are stationary, and that person, I mean, it could be us too. I mean, anyone who uses the interferometer can know. But let's say it's a bathtub, and this guy is actually looking. We have our eyes closed. This is we. We have our eyes closed, and this is the absolute observer. The absolute observer. So the absolute observer is stationary with respect to the medium. With respect to the medium, because we are tethered to the bank, but we don't know that we're stationary. Now, we could also be not tethered and stationary. I guess that would be even better. Oh my God, this is so confusing that only Jesus Christ can help us. This is killing me. Wait, all this time, what was I showing you? I wasn't sharing this. Oh my God, I wasn't sharing this. I hate it when this happens. So all this time, I wasn't sharing my screen. I was talking and talking and talking and talking and not sharing my screen. Great, let's start over. Let me see how much time has gone. 58 minutes. Yeah, let's continue, but this time I'll show you what's going on. Let's start again. So, imagine a bathtub. Here is a bathtub. Imagine a boat. Imagine it's moving at V. Imagine another boat that is stationary. Imagine. Let's ignore. It's too complicated. Let's ignore the second boat. So let's make it simple. So we have a boat. I don't want to. I do and I don't. Do I want to say that it's moving at known V? So I would say it's moving at V. We don't know. We don't know. Who's we? We are just a wave sensor. That's all that we are. We just sense waves. That's all we do. Now let's assume there's a boat here. It might be moving this way, that way. We don't know which way it's moving. We don't know what its dimensions are. We just don't know. 1 second. Message. What's going on? What is that? La 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 la. La 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 li la li la li la la la. La 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 la. La 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 la. No, I cannot take a phone call. What's going on? Ti la 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 la. Ti li la 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 la. La 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 la. Ti la 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 la. Let me check the audio. La 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 la. Yeah, it's good. Oh, we have Woody Johnson with us. Yeah, la la la. Woody Johnston. Morning, Woody Johnston. And la la la. Yeah, I'm waiting for someone to text me. I can see them. They're texting, but I don't know what they're about to text. They have a question for me. A question. Okay, so you're beginning to understand the complexity, the what's given and what's not given. So we don't know this velocity. We don't even know if there's a boat here. We don't know its length. And we don't know how time is ticking on the boat. We don't know anything. We don't know if the boat exists. We don't know. So this is basically a radar station. This is basically how a radar works. So we need to learn, or a sonar. So we need to learn how to operate. Let me see. Okay. La 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 no. I gotta take this call. Okay, 1 second. Let me tell them. 1 second. La 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 la. Hold on. Let me mute